Good morning everyone. Welcome to today's session. In last session we went through the process called nuclear fission and how the nuclear reactors work. In today's session we will see the phenomenon of nuclear fusion, which is the fundamental source of energy in sun and stars, what is its advantage over nuclear fission and how the fusion reactors work. So, let's begin the session. Now, let's see in detail what is nuclear fusion. As you may remember, nuclear fission was nothing but a heavy nuclei splitting into two lighter ones. Just opposite to that, nuclear fusion is the process in which two lighter nuclei fuse or combine together to form a heavy nucleus with release of large amount of energy. Both processes happen with ultimate goal of attaining stability. As earlier case, here also the mass on the reaction side, that is sum of mass of lighter nuclei, will be greater than mass of heavier nucleus. This mass difference is converted into equivalent energy that is released during fusion. Consider a single helium nucleus formed by the fusion of two deuterium nuclei. As following the earlier method, you can see about 24 MeV of energy is released per fusion. Nuclear fusion is also known as thermonuclear reaction. Do you know why? Just look at the fusion reaction mentioned earlier. Two nucleus has positive charge and there will be Coulombic repulsion between them. For fusion to occur, these nuclei must have enough energy to overcome this repulsion and come closer in the range of nuclear force, so that nuclear force will act up on them, binding them together to form a single heavier nucleus with release of energy. One of the way to provide this energy is to raise the temperature of the medium in which fusion occur to approximately 10 raised to 8 Kelvin. Since the fusion is possible only at that high temperature, the reaction is also called thermonuclear reaction. There are two possible fusion cycles, namely proton-proton and carbon-nitrogen cycle. Before going into that, let's see some features of the fusion reaction. We already discussed why fusion reaction only occur at very high temperature and why they are called nuclear fusion. As you may know, this high temperature and pressure condition is met in hot stellar bodies like star and sun, and hence fusion reaction is the source of energy in them. In fusion, the lighter nuclei co-MeV combine give lighter nuclei that are completely safe, unlike the radioactive fission fragment. And the energy released per unit mass of fusion 6 MeV is less than that for fission, which is 0.85 MeV. Also, the fuel for fusion reactor is abundant in Earth. These are few reasons why we choose nuclear fusion over nuclear fission as the ultimate source of energy. Let's take Sun. Earth from Sun at a distance 1.5 times 10 raised to 11 meter receives 1400 joule per meter square per second. This constant is called solar constant. Since we know energy received per unit area per second, we can calculate the total energy received in overall area as total surface, which is 4 pi times square of distance 1.5 times 10 raised to 11 times 1400 joule. We get total of energy received as 4 times 10 raised to 26 joule. This is exactly taken as the power radiated by Sun. We know per fusion, approximately 24.7 MeV, that is 4 times 10 raised to minus 12 joule energy is released. Then we can find the total number of fusion that occur in 1 second by taking ratio of power radiated by Sun to corresponding energy released per fusion. The calculation shows that about 10 raised to 38 fusion occur in 1 second. But it's not like the Sun will radiate power forever. When the fuel of fusion reaction, that is hydrogen exhaust, Sun will die off. Don't panic, few billion more years to go. Now let's move into the reactions of fusion. Recent modification of the estimates of the central temperature of the Sun now favor the proton-proton chain. In the pp chain, two protons first fuse to produce a deuterium nucleus, which combines with another proton to yield helium-3. Two He3 nuclei interact and form He4 and 2 protons. These reactions can be represented by the above equation. Total energy released during proton-proton cycle is 26.7 MeV. Not that there are no nuclear waste at the end of the reaction. Another fusion reaction that happens at the core of star is carbon-nitrogen cycle. The cycle goes like this: carbon nuclei fused with hydrogen nuclei to go to excited state that undergo gamma decay and positive beta decay respectively to form carbon-12 isotope. This carbon-12 isotope fuse again with hydrogen nuclei to form nitrogen-14 isotope that comes to ground state by gamma decay, again combine with hydrogen nuclei to form excited oxygen-15 isotope that undergo positive beta decay to form nitrogen-15 isotope. This isotope of nitrogen fuse with hydrogen nuclei to form carbon-12 isotope and helium nucleus. As you may note, we started from and ended with C12 nuclei. So carbon nuclei just act like catalyst. You know what is catalyst, right? It's a material that increases the rate of reaction without getting consumed. The overall reaction is nothing but 4 hydrogen nuclei fusing to form helium nucleus, 2 positron and neutrino, and energy of 27.5 mega-electron volt. It is estimated that the CERN cycle may keep going for another 30 billion years. Now we know in stars including Sun, hydrogen nuclei may fuse together to form helium nucleus. Then what about other heavier elements? How they are formed? Let's see how. There might reach a point where entire hydrogen fuse to become helium. At this point the star may contract due to gravitational pressure. As a result of contraction of star, the temperature will go beyond 10 raised to 8 Kelvin, which will mark the beginning of helium nucleus to form beryllium and carbon. Helium fusion reaction is also known as triple alpha reaction. At this point, do you remember the point we discussed while studying alpha decay? We said alpha particles are nothing but doubly ionized helium nucleus. Now look at the reaction. First 2 alpha particle combine to form beryllium. Later this beryllium combine with another alpha particle. Note that beryllium nuclei formed here is short-lived. It immediately split into 2 alpha particle. So, overall it's like 3 alpha particle fusion, hence the name. It is seen that formation of other heavier elements depend on the mass of star relative to Sun. Only hydrogen fusion is possible in small stars in which temperature can rise only up to 10 raised to 7 Kelvin. And in stars with mass in order of Sun's mass, temperature can go up to 10 raised to 8 Kelvin, so helium fusion can occur. Now if we consider stars heavier than Sun, temperature can be on 10 raised to 8 Kelvin, and hence may go up to carbon fusion. Carbon fusion can produce elements like oxygen, magnesium, etc. The heaviest element that can be formed by nuclear fusion is iron. Now, one might think, why can't this iron nuclei undergo fusion? Well, the reason is something you already know. Do you recall? It's the most stable nuclei with maximum binding. So any reaction of iron with other nuclei can only break iron nuclei. But if iron is the most heavier element formed via fusion, then how the elements with A greater than 56 formed? Well, the answer is that heavier elements beyond iron are formed by successive neutron capture and beta decay. Bismuth 209 is the heaviest element formed through these type of reactions. By end of formation 206 bismuth, neutron flux in star become insufficient for capture. At this point, star may explode, which is called supernova. During supernova explosion, neutron-rich nuclei may disintegrate into alpha particles. Electron-positron may combine to form neutron and neutrino particles. Neutron-neutron scattering may occur. As a result, neutron flux again built up. Thus by neutron capture, heavier element up to 260 are produced. Fusion reactor holds promise of meeting the energy requirements challenge of future. The fuel of fusion reactor, that is hydrogen and deuterium, can be easily extracted from seawater. And as we already know, in comparison with fission, more energy released by fusion process per unit mass. And we don't need to worry about disposal of nuclear waste, since byproduct of fusion reaction is helium nucleus, which is totally safe. Now we will discuss about reactions in fusion reactor, that is deuteron-deuteron and triton-deuteron reaction. In the experiments conducted by bombarding the particles deuteron and triton with the deuterons, the following reactions have been found to occur. Each of the deuteron-deuteron reactions 1 and 2 has a small cross-section. However, the deuteron-triton reaction, 3, is much more probable and also liberates a large amount of energy. The first fusion reactors are more likely to employ a deuterium-tritium mixture. Now let's see the conditions must be met via a successful fusion reactor. We know that for a fusion reaction to take place, the colliding particles should have enough energies to overcome the Coulombian repulsive forces between them. First condition is that temperature of approximately 10 raised to 8 Kelvin. At such high temperatures, the atoms are ionized into positively charged ions and electrons. This completely ionized and electrically neutral state of matter is called plasma, which is the fourth state of matter. In order to ensure frequent collisions between nuclei are frequent, there must be high density PF the nuclei. The reaction rate, which can be represented as 12 South African rand equals N1 N2 times average of sigma V12. Here N1, N2 represent particle densities of the colliding particles, V12, the relative velocity of the particles, and represents the average of the product of cross-section sigma and the relative velocity of the particles. If the colliding particles are identical, we have 11 South African Rand equals 0.5 North square average of sigma V. In order to ensure that the reactor gives more energy than the reactor's operation takes, reacting nuclei need to stay together for a long time. However, it is difficult to achieve a high enough particle density N for a long enough time tau in a hot plasma to obtain a net energy yield. According to the Lawson criterion, the product of the density and the confinement time, that is N tau of the plasma, should be about 2 times 10 raised to 22 particles and 10 raised to 20 particles second per meter cubed for the deuteron-deuteron and the deuteron-triton fusion reactions respectively to occur in it. We said fusion occurs at very high temperature. At that temperature the matter will be in plasma state. We cannot use ordinary vessel to confine them. Any contact with the wall of vessel will not only quickly cool the plasma but also cause the wall might evaporate. There are at present 2 schemes under investigation for confining the thermonuclear fuel. They are magnetic confinement and inertial confinement respectively. We will see them in detail. The first method for plasma confinement is magnetic confinement, in which plasma is confined by a carefully designed magnetic field. 2 classes of field geometry are magnetic bottle and tokamak. We will see both separately. Look at the figure on left side, it shows magnetic bottle. It is based on the reflection of an ion that moves in a magnetic field B whose lines of force converge. The magnetic force on an ion of velocity v is perpendicular to both v and b. So the force has a backward component in such a field as well as the inward component that causes the ion to follow a helical path around the lines of force. If the backward force is powerful enough, the converging field acts as a mirror to reverse the ion's direction of motion. Thus, we can form a high density of magnetic field lines which reflects the particles back into the low field region and is hence known as a magnetic mirror. A pair of magnetic mirrors constitutes a magnetic bottle. Yet another magnetic bottle for confining plasma is created by combining current flowing through external coil and current flowing through plasma, creating a toroidal magnetic trap. A toroidal field is produced by a winding of coils, and a poloidal field is produced by an axial current. These 2 fields are combined in the tokamak design. The resulting field lines form a helix, through which the ions can travel in closed orbits. Now that we have seen the method for confining plasma by magnetic field, now let's see what is the inertial confinement of plasma, and how it's different from magnetic confinement. In magnetic confinement, we used magnetic field. But in inertial confinement we employs energetic beams to both heat and compress tiny deuterium-tritium pellets. As you may see in figure, the fusion fuel in form of pellet is impeded by laser beam, high-energy electron or ion beam from all sides, so that intense temperature and pressure develop there, which is condition for fusion. But the difficulty with this method is that low efficiencies of laser or other sources, and the need to produce stable symmetrical implosion. Both the above schemes are in advanced experimental stage. The experiments have shown that fusion reactions can be initiated, but it has not been possible to extract the useful amounts of energy. So, as far in this session we saw what a fusion is, how it's different from nuclear fusion, advantage of nuclear fusion reactor and methods for confining plasma in fusion reactor. That's all for today's session. Thank you.